All right, let's get started here. The first thing we're going to discuss is what are called Diels-Alder reactions. Okay, these fall under a category of reactions called electrocyclic reactions. And that's because the electrons move in a circle in our mechanism. All right. So let's take a look at an example of a Diels-Alder reaction, kind of the simplest one we can have. Okay, we're closing out our conjugated dienes chapter. So one of our reactants is going to be a conjugated diene. And the other one is going to be what we call a dienophile. All right, let's pick apart this word here. What does that suffix "phile" mean? Nucleophile, electrophile, right? That suffix means a lover of something. So a dienophile is something that loves, aka will react with, a diene. All right? Our functional group of our dienophiles will always either be alkenes or alkynes. All right, and these will react together to form a six-membered ring. Okay, cyclohexene. And we just want to note that we will always form a six-membered ring in these Diels-Alder reactions, all right? They're a type of reaction where at first they look really scary, trying to keep track of which carbons is which, and then it's just really not too bad once you get it in practice. But the one thing you want to keep in mind is you will always get a six-membered ring as your product. We're just going to say, always six-membered ring as our product. Okay, so how can we figure out what the heck is going on in this reaction here? All right, so first of all, we want to change our orientation of our conjugated diene here. This is what's called the S-trans conformation, where both of those double bonds are pointed in opposite directions. That's our normal way of writing things out, all elongated. All right? And let's remember that although this molecule cannot rotate about those double bonds, it can rotate about this single bond here. Okay? So what we're going to do in order to see our products more clearly is to rotate 180 degrees about that single bond. And this will put our conjugated diene in what's called the S-cis conformation, where now both of those double bonds are pointed in the same direction. Okay? Your alkene must be in the S-cis conformation in order for this reaction to occur. Okay? Molecules don't really like going to this particular conformation here because then their two big groups are right next to each other. And so what you'll see in the lab is that molecules that are sort of locked in this conformation are way more reactive in these Diels-Alder reactions than a molecule where you have to wait for it to rotate into that correct conformation. Okay? But anytime we see our conjugated diene, the first thing you're going to do is rotate it into this S-cis conformation. All right? Because this is how we're going to sort of see how this reaction is going. All right? And we're also going to just sort of on the paper rotate our diene so that it's lined up our dienophile, so that it's lined up as well. Okay. In our reaction here, our electrons are going to be moving in a circle. So what we're going to see is one pair of pi bond electrons from our diene comes out and attacks that carbon on that dienophile. This pair of electrons comes and attacks the carbon on the diene. And then this pair of electrons will move into that new position for our double bond. So you see that in our mechanism here, we have our electrons that are moving in a circle. Okay? Personally, I don't think the mechanism for these are all that terribly helpful when looking at the product. Okay? I mean, we need to know that they move in a circle, but this isn't a reaction where when I think about it, I automatically go in my mind's eye to the mechanism, like I do for those electrophilic addition reactions. Those are very well explained by the mechanism. Okay? So here, let's take a look. Let's just make sure that we can keep track of who's who. We said that this should form this cyclohexene product here. So keeping track of which carbons are which here. Importantly, these 4 carbons about my double bonds in my conjugated diene will make up these 4 carbons in my Diels-Alder product here. Okay. Then these 2 carbons in my dienophile will make up the other 2 carbons in my 6-membered ring. All right, so these are the carbons that we need to keep track of here in our reaction. If we look, we have a new sigma bond that's formed, a new single bond between the orange carbon in my diene and the green carbon in my dienophile. So that's this arrow right here. We have a second new sigma bond. That would be this arrow right here. Okay. And then lastly, what we see is our pi bond has moved in this electrocyclic reaction. If I count my carbons just to kind of keep track, originally I had a double bond between carbons 1 and 2 and a double bond between carbons 3 and 4. Now my double bond is located between carbons 2 and 3. So this right here is where we moved that pi bond pair of electrons. Okay, so what we will see, again, we always get a 6-membered ring in this reaction. Why do we always get a 6-membered ring? Because our 4 carbons in our diene will always react with 2 carbons in that dienophile. All right, and depending on, we just picked a 4-carbon diene and a 2-carbon dienophile. So this would be sort of the simplest Diels-Alder reaction that we could have here. All right, let's see if we can't form our products Okay, I'm going to give you another diene, but now I'm going to decorate it with some methyl groups here. And we're going to react this with our alkene dienophile. All right, everybody take a second and see if you can't draw me the product for this reaction here. right, so the first thing I'm going to do is I'm going to rotate my diene so that it is in that correct conformation. I want those two double bonds pointed on the same side here. Right, so you're always going to sort of start by orienting your diene. So again, in this what we call the S-cis conformation here. Okay, and importantly, it is these 4 carbons about this double bond, about this conjugated diene, that are going to be involved in my electrocyclic reaction. I have these 2 other methyl groups that are just kind of along for the ride here. All right, so then when I form my new 6-membered ring, this is a great place to start when drawing your product, because you're always going to form a 6-membered ring in these reactions, right? So start there. We want to map our carbons here. We said that these 4 were from our diene, so that means these 2 are our dienophile. All right, I'm not done yet. I want to remember that this double bond in this reaction is going to move Cool, and then the last thing I need to do is just decorate it with those extra carbons. So again, I'm starting from that 6-membered ring, and then I'm just filling in all of my carbons that I need. You can kind of keep track, 1, 2, 3, 4, 1, 2, 3, 4. Again, I'm not numbering for my nomenclature here, I'm just numbering to help me keep track of who's who. And I can see that I'm going to need to include a methyl group on carbon 2 and a methyl group on carbon 3 in order to get my product drawn correctly. Okay, so again, you're always going to have this 6-membered ring. You want to start with that 6-membered ring, right? You're always going to have the 4 carbons in your conjugated diene that are going to make up these 4 carbons in your ring, and the 2 carbons in your alkene or alkyne about that double or triple bond. That will be in my, those are the other 2 carbons in my 6-membered ring here. Okay, so again, it's a little intimidating looking, I think, when you first look at it, but once you get in and start practicing, it's not too bad. The one thing you want to keep in mind, the one starting point, is you're always going to have that 6-membered ring as your product. Okay? All right, cool. So we did a dienophile that was an alkene. Let's do another example here using a dienophile that's an alkyne. Okay? For my diene, I'm going to use a molecule that is locked in that S-cis position. So it would be very reactive in our Diels-Alder reactions. Right? So this molecule right here, these double bonds, because of that ring, they can't really rotate out of this conformation. So this would be a great diene to use in these reactions here, because it's already stuck in that correct conformation. All right, so now we're going to do a triple bond. We'll put some methyl groups on that. Okay, again, for my product, I'm going to start with that 6-membered ring. All right, I want you to take a second and to map. This is my new ring here. Which carbons on this side correspond to the carbons on the left-hand side? Okay, just by analogy of what we did above. The 4 carbons about that diene, about that conjugated diene, are going to make up 4 carbons from my ring. The other 2 carbons in my new ring are going to be the ones that were about that triple bond. Okay, so I'm obviously not done here. I got a bunch of carbons missing. All right, I also have some pi bonds missing. All right. Remember, we said because of our movement of electrons here that we have this new pi bond that forms on in my product side. Okay, but if we finish out our mechanism here, okay, what we're going to see is it's only one of those pi bonds in my alkyne that are reacting to form a new sigma bond. So I'm still going to have one left over. All right, so that's the big difference of using an alkyne as your dienophile. We're going to retain one of those pi bonds in our product. Okay, so then take a second and see if you can't draw in the rest of our missing carbons here. Right? So my reactant had a 6-membered ring. I formed a new 6-membered ring in this product, but I'm not going to get rid of the original one. So this would be these two fused rings side by side. Is there anything else I'm missing? All right, always count your carbons. I do not have the same number of carbons on the left-hand side as I do on the right-hand side. In particular, these two from my dienophile are missing. So I need to put those on there. Okay, so here is my new 6-membered ring that's formed. I've decorated it with with all the other carbons that were in this reaction. All right, and because I used an alkyne, I still have one of those pi bonds left over between those purple carbons when I form my product. Okay, so the last thing we're going to learn about these Diels-Alder reactions is that they preserve stereochemistry. So what do I mean by that? Let's do another example here. We'll do our diene. Okay. And now I'm going to react it with an alkene, but an alkene with a specific stereochemistry. So I have these two chloro groups that are pointed on the same side. All right, everybody take a second and see if you can't draw me the product of this reaction. Well, we'll fill in our stereochemistry here at the end. But just to practice rotating about that single bond and forming your new 6-membered ring in these Diels-Alder reactions. All right, so I'm going to draw my product. I'm going to start with that ring. All right, notice how I've always done the same procedure here where I start by drawing my 6-membered ring, and then I say, all right, these 4 carbons must be those 4 carbons about my conjugated diene, and these 2 carbons must be my 2 carbons in my dienophile about that double bond. Okay. One thing to note as you get like these more complicated molecules and you're picking them up and spinning them around, obviously model kits are amazing for this sort of thing. Okay. The other sort of double check is I'm allowed to rotate about this single bond, but you can't rotate about a double bond, right? So the stereochemistry that I see in my double bonds above has to match what it is below. So what I mean by that is if I go in and I apply my rules for stereochemistry, this one's an E, and this one's an E. Well, that has to be preserved down here as well, right? I can't flip about that double bond. I'm just rotating about the single bond. Okay, so then to fill in my other carbons on my orange, boom, I got that double bond, that pi bond that's moved. Cool. All right, so now we got to go to that preserved stereochemistry bit. What do I mean by that? That means that a cis alkene, actually let's be even more clear, cis dienophile will give you a cis ring. All right, both of those groups will be pointed in opposite directions. And likewise on the flip side, if you started out with a trans dienophile, you would get a trans cyclohexane ring. All right, so since my 2 chlorines are pointed on the same side, right, this is a cis alkene. That means when I draw my product, I'm going to make sure to draw in the stereochemistry of that ring and show that they are pointed on the same side. Okay, so we get this stereo-specific product because we started out with a stereo-specific alkene, a stereo-specific dienophile. All right, cool. Let's do one more, just for the sake of practice, because I know these are intimidating. right, so I rotated that diene into the correct position here, so now I can draw my cyclohexene ring. All right, and I'm going to say these 4 carbons here are going to be these 4 carbons here. These 2 will be these 2. All right. I need to put in my moved pi bond here, and then I need to decorate with all those methyl groups that are about my diene. So if I look, carbon 1, 2, 3, and 4 all have a methyl group. Okay, in my dienophyl, my 2 carbons also each have a methyl group. But because that stereochemistry is preserved in this reaction, I have to specifically indicate that stereochemistry in my product here. So I'm going to indicate that one bond is pointed out of the page and the other bond is pointed into the page, right? My trans ring here. Cool. All right, practice is going to make perfect with these ones. I know that they're a little ugly looking because you get these products out of here. I mean, that's kind of a theme of the second semester versus the first semester. First semester, you're like swapping an OH group for a chlorine or something. It's kind of easy to keep track of who's who. We're going to do a lot more chemistry that makes new carbon-carbon bonds in this semester. And anytime you make a new carbon-carbon bond, your product is necessarily like bigger and uglier than what you started with, right? So again, breaking it down to keeping track of who's who, which carbons are which, as I go from reactants to products, is going to be much more of a skill that we need in this second semester. Cool. All right, we're going to now switch gears and we're going to introduce the next chapter. Chapter 15, which is all about something called aromaticity. And we won't actually talk about what the heck aromaticity is until next chapter. Until next lecture. But we'll talk about this one sort of star of the show here when we're talking about aromaticity. And that is that 6-membered ring where every other bond is a double bond. Okay? Does anybody know what this one's called, this molecule here? It's got its own special fancy name. Benzene. Cool. Okay, in the history of organic chemistry, benzene was really, really important in demonstrating sort of the idea about these conjugated pi bonds. Notice here that we have a bunch of pi bonds that are conjugated, but not only that, the whole ring is sp2 hybridized carbons, right? Yeah, so anyways, plays a very outsized role in terms of the history of how we got a bunch of our theories in organic chemistry. Practically speaking, it is a well-known carcinogen, so you don't handle it in the lab quite as often as they used to before they realized how bad it was for you. Oftentimes, you'll use some sort of a derivative of a benzene, and they tend to be a lot safer. Benzene has a very great time getting into your cells and wedging its way between your 2 DNA strands, your bases in your DNA. So it Fs up, it really just kind of makes its way in and Fs up your genetic code a little bit, as do most carcinogens, okay? So we don't handle it too much. Usually in the lab this semester, you'll probably work with some sort of a derivative of benzene. It's got a different functional group sticking off of it, but nonetheless, this is sort of gonna be the star of the show here is benzene. And so first thing we're going to do is we're going to talk about nomenclature of benzene. All right. So what do I mean? Obviously, if it's just the six-membered ring, you call it benzene, right? But what do I call this molecule here? We have our benzene ring, but now I'm going to decorate this thing by sticking a propyl group on there. All right, so we got our rules for nomenclature. Same rules that we always do. Step 1, find and name that parent chain. Okay. In the case of our benzene derivatives, the parent chain is always going to be benzene. Or what we're going to call our special benzene derivatives. And I'll explain what I mean by that here in a second. We'll complicate things here in a second. All right, so step 2, you're going to find and name your substituents. Okay, so my parent chain here is that benzene ring. My substituents are what's sticking off of that parent chain. What would we call this alkyl substituent here? 3 carbons would make this a what type of group? A propyl group. All right. So then we get to this stage where we number our parent chain. But much like for cyclohexene or cyclohexane, all of our cyclic alkanes, if you only have one substituent on there, you don't indicate the position of that substituent. It's always going to be on carbon 1, right? If I picked up that propyl group and moved it to another carbon on benzene, we would just renumber that benzene ring. So that would become carbon 1. So for what we call monosubstituted, benzenes, we have no locant in our name. All right, I'm going to leave a bunch of space here under our numbering of our parent chain. That's going to be the thing that's a little bit trickier, at least a little new to us here in this particular chapter. So then lastly, you just put it all together. Okay, so this thing here would quite simply be propyl benzene. Again, I'm not going to put the locant in my name. There's only that one propyl group, so I know it's on carbon 1 in my molecule. All right, so I want everybody to take a second and name this benzene derivative for me. All right, my parent chain is that benzene ring. I have this bromine sticking off of it, which is a bromo group. So this is just bromobenzene. All right, no locant because it's just a monosubstituted benzene derivative. All right, cool. So now let's take another example. And now we're going to put two substituents on there. All right, two bromine groups. And depending on where I put those two bromine groups, this molecule is going to have them all spaced out a little bit differently. They could either be right next door to one another. Okay, they could be one removed, or they could be on opposite sides of the ring. Okay. For your cyclohexane derivatives, this is when you would start having to number the ring because, again, you got to indicate the separation of these two groups here. Right? These are three different molecules with three different physical properties, different boiling points, et cetera, et cetera. Okay? For benzene derivatives, we have a special way of doing it. All right? You could call this 1,2-dibromobenzene, but that's not how they do it in the benzene world. They have specific sort of little names that they use. This would be the ortho. This would be the para. And I'm sorry, the ortho, meta, and para. All right, so this would be ortho dibromobenzene. You'll also see it with just the O dash dibromobenzene. This would be the meta dibromo. Or M dibromobenzene. All right, and when those two groups are on opposite sides of the ring, it is the para dibromobenzene. Or P dibromobenzene. All right, and so we said for monosubstituted ones, we don't have to include the locant. For di-substituted benzenes, we're going to use this ortho, meta, or para designation. All right, and again, let's say that I have some sort of a group here on my benzene ring. The ortho positions are the ones located right next door. So these would both be ortho positions. The meta position is when there's one carbon in between. So these would both be meta positions. And the one on the opposite side of the ring is that para position. Okay, So specifically for these di-substituted benzenes, we're going to use this ortho-meta-para designation instead of building the numbers into your name, right? This will be there instead of any numbers. If you have tri or more, then you just use your regular numbering. All right, ortho, meta, para, it doesn't make sense if there's greater than 2 substituents on this ring. It's specifically for 2 substituents to tell you how far apart they're located on this ring. Right? If you have any more, if you had 3 chloro groups, then you're just going to go to your regular numbering just like you did with cyclohexane. Okay. Cool. One more sort of functional group to introduce to you guys, because this one's going to be very important for this particular chapter. Okay. This NO2 we're going to see a lot. And this is what's called a nitro group. It's got one of the cooler names. All right, so this molecule here with its just one functional group would be nitrobenzene. All right, importantly, you'll see it all condensed and nice like this, but let's draw out the full Lewis structure of this group here. Okay. What you have is the nitrogen in the middle, and it's bound to these 2 oxygens. Okay. One of them is double bonded, whereas the other one is just single bonded. All right, I was good and I filled in my lone pairs here. What else is missing from my structure? The charges. What would the charge on the nitrogen be? Positive. And what about the charge on this oxygen? Neutral. And what about this oxygen? Negative. All right, so you see you got a bunch of formal charge in here, but it's all balanced out. We have a plus side on our nitrogen and a minus side on our oxygen. And this is nice and stable because of resonance, right? Typically atoms would not be super pumped to hold a formal charge, but we can stabilize that formal charge through resonance. And what you see is this pair of electrons would come down here, kick that one up there. So that's how we can get away with all this formal charge in this molecule here, because it's resonance stabilized. We'll talk a lot about the properties of this molecule as we move on here. For right now, we are just kind of introducing it so we know how to name these things. Okay? Cool. So last sort of complication, and we'll pick up with this next time, but I just want to sort of give you guys a teaser here. We said that it's always going to be, the parent chain is always going to be benzene or one of our special benzenes. So what the heck do I mean by that? Well, there are certain benzene derivatives that have functional groups on them that get their own fancy name. All right, so let's just take a look at one. If we take a benzene derivative and we put an alcohol group on there, a hydroxyl group, this is not like benzanol or something like that. This molecule has its own special name, and that is phenol. And so if we take a derivative of phenol, let's put a chloro group on there. All right, the parent chain is not the benzene ring, it's the entire phenol portion here. This becomes the parent chain in this molecule. So there are certain benzene derivatives that have functional groups on them that we're going to learn special names for. And those special names become our parent chain in our molecule. All right? So this one here is not going to have benzene in the name. This one would be chlorobenzene. phenol. And I'm not quite done yet because I got these two substituents on there. So what are these two located? Ortho, beta, or para from one another? So right next door, O-M-P, right? O-M-P. That's how I remember it, in order. Like O-M-G, but O-M-P, all right? Cool. So in this case here, we are located in that meta position. So this would be meta-chlorophenol or M-chlorophenol. Okay? So what we're going to call it there, but next time what we're going to do is we're going to introduce a few special benzene derivatives. And again, what we're going to see is that they will become the parent chain in your molecule. What's up?
So for this conjugated, when I was looking at this reaction, I was just thinking at first probably the bromine would need to go here because it's more substituted.
Right, but remember what
Yeah.
beats out being more substituted is being allylic.
Oh,
The
that's
carbocation
the
will
reason why.
always form in the allylic position. It doesn't
Okay.
matter if this carbon's more substituted or less
Okay.
substituted because allylic
Oh,
beats everything else.
Okay, I see. So yeah, I was just thinking to want to add an